So this video is going to talk about tangential quantities. So basically, if you have an object that's rotating, you can relate the translational motion, right? So displacement, velocity, acceleration, and so on, to the angular motion, angular displacement, angular velocity, and angular acceleration. And this covers chapter 12-4 in the textbook. Okay, so the tangential quantities. So first off, if you just want to know, so say you've got some point P on a rotating object. Well, if you want to know how far it travels, you can relate that to the angular displacement delta theta. And the distance traveled is going to be delta theta times the radius r. So where r is the distance between the point and the axis of rotation, right? And this actually is just, you could think of this as just the definition of the angle. So remember, we defined angle as angle was arc length over the radius. So, and our distance traveled is really just the arc length here. So it's the angle times the radius. So then you can, once you know this, you can relate the angular velocity to the tangential linear speed, because the tangential speed, so the green arrow in the diagram here, so we got some point P and its instantaneous velocity is going to be this green vector V. Well, it's the time derivative of the distance traveled, which, sorry, I switched letters here. So I called it distance traveled D up here, but I'm using L since that's actually what they use in the book, in the image here, this DL. But that, right, so basically you take the time derivative of this delta theta times r, so that's just d theta dt times the radius r. D theta dt, remember, that's just the definition of our instantaneous angular speed. So the tangential speed v sub t is the radius times the angular speed omega. So then you can do something similar for the angular acceleration. So the angular acceleration must be related to the tangential linear acceleration, and angular acceleration, there we go. Well, the tangential acceleration a sub t, so that's the acceleration in the tangential direction, right? So tangent to the circle. And that's just dv dt, where this is now the time derivative of the tangential speed v. Well, but the tangential speed v, remember, was r times omega. So r, we assume r is constant. So this is r times d omega dt. And remember, d omega dt is the angular acceleration alpha. So the tangential acceleration a sub t is r times the angular acceleration alpha. Now, just a little side note here. So if you could also define total acceleration. So let's say you've got a point P on a rotating bike tire. So P is moving around in a circle. Now, from before, we know that any object moving in a circle, so uniform circular motion, so if omega is constant, right? So the tangential speed is constant, then it's still going to be accelerating, right, since the direction is changing. And we called that the centripetal acceleration. So while your book uses a sub c, the textbook I stole this from likes to use a sub r. It's the same thing, right? So centripetal acceleration points in towards the center of the circle. Now, in addition to that, if it's now non-uniform circular motion, well, it could be speedy, it could be rotating faster and faster, or it can be slowing down. So in that case, there's also going to be some tangential component to the acceleration, a sub t. And then the total acceleration is going to be the vector sum. So you've got the radial or centripetal acceleration, a sub r, plus the tangential acceleration, a sub t. The sum of those two vectors is the red arrow here, so that's your total acceleration. Okay, and so, right, so if you need to get the total acceleration, you take the vector sum of the centripetal acceleration and the tangential acceleration. Okay, and just a couple other useful things. I think we've mentioned these before, but just a quick reminder. So if you're interested in the centripetal acceleration, also called the radial acceleration, so remember from before, well, it's going to be the tangential speed squared divided by the radius r. Well, but the tangential speed we saw was r times omega, so you square that and divide by r. So you can also write the centripetal acceleration as r times omega squared. So, and again, quick reminder, so you can also define something called the frequency. So the frequency, or sometimes called the angular frequency, or actually no, this is just the frequency, is omega divided by 2 pi. So essentially what you do here, omega, remember, is in radians per second. You divide by 2 pi, and remember there are 2 pi radians in one complete rotation. So frequency then is, the units are technically 1/seconds, or you could think of it as revolutions per second. So that's what frequency is, the number of revolutions per second or per time. And you can also define the period, and the period is always the reciprocal of the frequency. So if frequency is revolutions per second, the period is seconds per revolution.